Hello everyone, this is going to be problem 1. Change the order of integration and evaluate 0 to 1 root x to 1 of e to the y cubed dy dx. For these problems, I always like sketching it out. It just makes it so much and that much easier to see the bounds. So y is going from root x to 1, so kind of like that region right here, and then x is 0 to 1. And to rewrite the integral, we don't really know the bounds, but we know it's going to be e to the y cubed dx dy, and that means we're going to find the x bound, and it looks like it's going to be going from 0 to that curve right there. So if we rewrite the curve, we have y equals root x right now, but we want it to be like x equals something. So x equals square both sides, x equals y squared. So 0 to y squared, and then this line right here, as we know, it's y equals 1. So 0 to 1 is y. And this should be actually possible this time. So we're going to get, evaluating the inner integral, we're going to get y squared e to the y cubed, but the integral of that from 0 to 1 dy, and that is just e to the y cubed 1/3 from 1 to 0, and that is 1/3 e cubed, I believe, no, sorry, e to the first minus 1, and that is D. Number 1, the answer is D. 2, find the maximum of f(x,y) equals x plus y on the curve defined by x squared plus 2y squared equals 6. So whenever we see that, we just know Lagrange multipliers. We should be thinking that. This one's pretty easy because we have 1 and 1 here. So 1 equals lambda times 2x, oh, what was that? And 1 equals lambda times, for y, that is a 4 right there. And since we have this curve, we can always solve for the x and y here and plug in, and it should be a pretty easy solve. So we're going to get x equals 1 over 2 lambda, and y equals 1 over 4 lambda. So we're going to get, plugging in here, we're going to get, sorry, that erased. We're going to get 1 over 4 lambda squared plus 2 times 1 over 16 lambda squared equals 6. Combining our fractions, we're going to get, this is going to be 2 over 8 lambda squared plus 1 over 8 lambda squared. That equals 6. And 3 over 8 lambda squared equals 6. And we can just kind of see that 3 over 48 equals lambda squared, and therefore lambda is just going to be, or sorry, this is just 1/16 equals 1/16, so lambda is going to be plus or minus 1/4. And since we have these like values right here, we can just plug lambda in there and get our values. And it looks like since our function f of x, y is just x plus y, we're just going to take the positive value of lambda, which is just 1/4. And when we plug it in, we're going to get x equals 2 and y equals 1. So adding those together, because x plus y, our answer is 3. Number 3, evaluate the integral, double integral of the region R, 2xy squared over x squared plus 1 over this box right here. So this is pretty easy, hopefully, and we just kind of need to just write out the integral, and 2x y squared over x squared plus 1. I'm going to go dx dy. Does not really matter since it's a box. This is going to be our x range, so x is from 0 to 1, y is from 0 to 2. And it doesn't really matter which way you integrate it. Should end out the same pretty much. So since we have kind of x squared plus 1 here and 2x, I'm just thinking ln, and we even have ln in the answers, so that's a little trick right there. So it's going to be ln, absolute value, doesn't really matter in this case, but x squared plus 1, obviously y squared, integral of that, and x is evaluated from 1 to 0, y is still the integral 0 to 2. And that gives us ln 2 minus ln 1, which that's just 0. So we're going to get y squared ln 2. There we go, that again, 0 to 2 of, whoa, that is, yeah, okay, dy. And that is just y to the third over 3 ln 2. And evaluate it to 2 to 0, and that is just 8 thirds ln 2. And that is D. Number 4, D is the region between the circles x squared plus y squared equals 1 and x squared plus y squared equals 2. Find double integral of the region D, e to the x squared plus y squared dA. So, I mean, we have circles. We should be thinking polar coordinates. This r equals 1, r equals root 2, and this exponent right here is just r squared in polar coordinates. So if we write it out, double integral here, e to the r squared, and we have to remember that dA is r dr d theta. Theta is from 0 to 2 pi because just between the circles and circles are by definition 0 to 2 pi. R, like I said, 1 to root 2. And it's worth noting that since nothing depends on theta in the actual integral, we can just take out the 2 pi. We can just top minus bottom, and in this case, it's just 2 pi minus 0, which is just 2 pi. And then integral of this thing right here, r times e to the r squared, is just going to be e to the r squared, all right, 1/2 of that. And I guess we can just cancel that out. Evaluate it at root 2 to 1. We're going to get pi times e squared minus e. And that is c. Just by distributing that, we're going to get the same answer. Number 5, which of the following does not equal the volume of the solid bounded by x equals 0, y equals 0, z equals 0, and 3x plus y plus z equals 3? All right, so this is a pretty annoying problem. I don't really like these problems because just one small thing is all that takes to make an answer wrong. So A looks right. And what we're pretty much doing here is we know that if we have the first variable, we're just going to solve for the variable. So like in this case, I would do dz personally here. So like d did dz first. So I literally just solve z equals 3 minus 3x minus y, and that's what's right here. And then to get like the next bound, all we're going to do is set the top bound equal to the bottom bound and solve for whatever respective variables next. So I believe the answer here is going to be E, and that's because when you're solving for x here, we're going dx, so we have to solve for x, obviously. It's not going to be equal to that. So if 3x plus y plus z equals 3, solving for x, we know that we're going to have something over 3, so that is not going to be correct. So 3x equals 3 minus y minus z. So yeah, it should not be this. It should in fact be x equals 1 minus y over 3 minus z over 3, and that is not what's given over here. So that is the wrong answer. So that makes it E, the correct answer, in fact. All right, number 6. Evaluate the triple integral, the region D, 2z dv, where D is the region between z equals square root 4 plus x squared plus y squared, and z equals square root 12 minus x squared minus y squared. All right, so it's a triple integral this time, and we still have x squared plus y squared, so I'm thinking cylindrical coordinates here. And if you just kind of look at the shape, we know it's going to be some sort of cone. It might be a little shifted up, but that doesn't really matter for our use case. And looking at the other one, that's just going to be a sphere, so the top half of the sphere. So if we kind of think about it, it's kind of going to be an ice cream cone. Z is going to be kind of this thing right here, and then R is going to be, we actually need to find the intersection between the two surfaces, and we can do that pretty easily. So I'm just going to sub in R, or R squared, for x squared plus y squared, just to make it a little bit easier, and to find the R value. We know R is going to start at 0, but we need to find these ending values. So we have z equals square root 4 plus r squared, and z equals square root 12 minus r squared. And then setting these equal to each other, 4 plus r squared equals 12 minus r squared. 2r squared equals 8. R squared equals 4. Therefore, r equals 2. So our r is going to be from 0 to 2. Theta is probably going to be 0 to 2 pi because cones are all around. So I'm just going to write out the integral and make it easier. It's going to be 2z r dz dr d theta. Theta, like I said, 0 to 2 pi because we're going all around the circle. R is 0 to 2. We solve for that. And z is going to be square root the top minus the bottom. So the top in this case is going to be our cone. So it's going to be, whoa, that is not good. It's going to be 4 plus r squared. Our bottom is going to be 12 minus r squared. Or sorry, our top is going to be the ball or the sphere, 12 minus r squared. Okay, so like I explained in the previous problem, since nothing depends on theta here, we can just do top minus bottom for theta and take that out as a constant. So we're going to get 2 pi. And in fact, since nothing depends on r here too, or no, actually the bounds depend on r, so we can't really do that for r in this case. But it still should be pretty easy. Leaving r on its own, I'm just going to do the integral with respect to z, and you'll see why in a second. So we're still going to have 0 to 2. Integral of z squared, or 2z is just z squared, and we need to evaluate that at 12 minus r squared, and 4 plus r squared. This is still r dr, and the squared is going to be very nice to cancel out all these disgusting square roots. So we're going to get 2 pi integral 0 to 2 r times top minus bottom, and that's just going to be 12 minus r squared minus 4 minus r squared dr. And just simplifying that, we're going to get 8r minus 2r cubed, I believe, hopefully. Yep, that looks pretty correct. And we obviously need to integrate that 0 to 2 dr, and obviously the 2 pi out in front. So that's just going to be 4r squared minus r to the 4th over 2, and that is from 2 to 0. Plugging that in, 0 doesn't matter, so we don't need to consider that. We're going to get 16 minus 16 over 2, 8, which is just 8. Don't forget the 2 pi, so we're going to get 16 pi, or 8 times 2 pi equals 16 pi. And that is A. Number 7, rewrite the triple integral 2 to 6, 0 to root 2, x, I believe, it's a little bit janky, the PDF scan, x to square root 4 minus x squared, e to the negative x squared minus y squared, dy, dx, dz, in cylindrical. So they're saying that. Hopefully we already knew that. But, okay, so I think that z doesn't really matter. We don't need to consider that just because it's just going to be 6 or 2 to 6, and we can confirm that observation in our answer choices. They're all the same. Whoa. Oh, that was pretty cool. Okay. So yeah, and same with r, I guess. But we can kind of know that this thing right here is r equals 2. So that does not really matter. But sketching out kind of our dy dx region. Oh, I'm on shape mode. Okay, that makes sense now. Dy dx, we're going to get y is going from y equals x, so that's just the straight line, to y equals square root 4 minus x squared, which is just this thing right here of radius 2, the top half of the circle. So that confirms why r is 0 to 2. And just looking at our answers, e is not correct because there should be an r here. D, same reason. And now we're just going to find theta. And it looks like x is going from 0 to root 2, so we're just really concerned about this region right here. And as we know, the line y equals x, if we think about it, that's where, if you think about the unit circle, but I don't really like to think about that, this angle is going to be equal to this angle, and that's only at pi over 4. So our lower bound should be pi over 4, upper bound pi over 2. And that looks like C is our correct answer. It's not 0 to 2 pi, obviously, and it's not 0 to pi over 2. That'd just be this region here, right here, and that's not what we're looking for. So C. Number 8, choose the triple integral in spherical coordinates that represents the volume of the solid bounded by the curve, or the cone, sorry. Z equals square root x squared plus y squared, and the sphere x squared plus y squared plus z squared equals 8. All right, I love spherical coordinates. B is incorrect because we know it should be rho squared sine phi, not rho sine phi. C, again, something is wrong with this part. It should be rho squared sine phi, not sine squared. So, all right, and it looks like all our other answers, everything else looks good. Okay, the cone z equals x squared plus y squared is just like the standard cone. So if we draw kind of like the cross section, we're going to get like something like this. And that means it should be 0 to 2 pi because we're going all around. And yeah, all our answers are 0 to 2 pi, so we don't need to consider that, really. And then we have that sphere of radius root 8. So A is not going to be our answer because rho is not 8, it is root 8. And now I guess it just leaves it up to our phi value. So just looking at it, if we draw our sphere like this, we're only concerned about the top half, and this is going to be the phi that we're looking for, and that's just going to be pi over 4, kind of for the same reason the problem above, since we have the standard cone where there's no like value. So if there was a value like 4 x squared plus y squared, that'd be different, but this angle right here is going to be equal to that angle, and that can only happen at pi over 4. So this is pi over 4, and so is phi right here. So phi is going to be 0 to pi over 4 in this case, and that is D. Number 9, which of the following is a radial field? So as we know, a radial field is just kind of a field where at each point, or not at each point, but it should be going kind of out at all directions. So this is kind of like what I was thinking, like an electric field. I don't know if you guys have experience, but this would be like a positive charge, but that does not really matter. We are in math, not physics. So just looking at the answers, that means that at each point we should have some sort of like yx vector, and that makes B, C incorrect because that would just be, that's yx, not xy. So that would be the opposite direction, and that would not be a radial field in this case. And so is D, because we're not going to be including those negative components just because we're going x squared, and that just means the resultant would be all positive, and that's not what we want in this case. And E is also wrong because same reason, x squared, that gets rid of pretty much all of the negative values. And A looks like our answer. By default, like the radial field like should have some sort of x, y, and then this thing right here in the front doesn't really matter because it's just a constant, and we're really only concerned about the direction of the, I guess, field lines or the vectors. So that doesn't really matter. That just makes it a little bit smaller and doesn't really do anything with the actual direction. So A is our answer. Number 10, find the center of mass of the rectangle. 0 is less than x is less than 1, 0 is less than y is less than 2, where the density function is given by rho of xy equals xy. All right, so we know we need to actually find the mass first. So that's just the integral over the region of the density. Xy dy, or I'm going dx dy, doesn't really matter in this case. X is 0 to 1, y is 0 to 2. Integrate x, we're going to get x squared over 2 times y from 1 to 0, and that's just basically 1/2 y, and then integrating that from 0 to 2 dy, we're going to get y squared over 4. That means our mass is just equal, I guess from 2 to 0, our mass is just 1. So that makes it very easy, and just looking at our answers, we only really need to find one of the components, and I'm just going to do the x component because that is the first one. And to find the x component, we need to find kind of the moment of inertia about the y-axis actually, and that's just given by the distance from the y-axis, which is just the x-coordinate. So that's just going to be x times rho of xy, and we need to integrate over our region. So that's just going to be same region, so same bounds, 0, 0, 1, 2. It's going to be x squared this time because we're multiplying rho of xy by 2. X squared y dx dy. In this case, it's going to be x squared over 3, y, evaluated at 1 to 0, still integral 0 to 2, and that is the y. So that's just y over 3, integral 0 to 2, dy. And that gives us x squared over 6 from 2 to 0, which is just 2/3. And hopefully that's one of our answers. Okay, D is our answer because none of the other ones have 2/3 as their x coordinate. And we could do the y component, or the y coordinate, just to check. And that would just be given by y times rho of xy. Same integral bounds. Number 11, consider a spring whose shape is a circular helix. 1 over root 2 times cos t sine t. T goes from 0 to 6 pi. And mass density of the spring is rho of xyz equals 1 plus x. Find the mass of the spring. So we know that this is just going to be integral over like the curve c, or whatever, r of t. And it's going to be magnitude of r prime of t. Whoa, what happened there? Times r prime of t, and times rho of t dt. And now we just need to compute the magnitude of r prime of t, which should be pretty easy. So r prime of t equals 1 over root 2 times negative sine t cos t 1. And it looks like r prime of t is going to be square root. Looks like it's going to be 1, but just to confirm, we're going to get 1 over 2 sine squared t plus 1 over 2 cos squared t plus 1 over 2. And yes, it is indeed 1, which is honestly very nice. And that's just because sine squared t plus cos squared t equals 1. And factoring out 1/2, we get that. Very nice. So we don't even need to consider this at all, but I'll still write it out. Now, rho of t is just, we just need to plug in the z component of r of t. And that's actually not just t. And I realize that now, but when I was recording, I did not realize that it is actually t times 1 over root 2, because technically you need to multiply them to get the real r of t. This is like the fake r of t. So rho of t equals 1 plus t over root 2. And now we just need to integrate that from 0 to 6 pi, sorry. 1 plus t, that looks too much like a t. T over root 2 dt, and that is just t plus t squared over 2 root 2 from 6 pi to 0. And that is just, we don't need to worry about the 6 pi because that will all cancel out. That is just 6 pi minus 36 pi squared over 2 root 2. And that is just 6 pi minus 18 pi squared over root 2. And hopefully that's an answer. Yes, that is E. Nice. Number 12. Let F be a force given by f of xy equals yx. Compute the work of this force along the curve C. This curve is t, 4t minus t squared, with t is less than or equal to t, or 0 is less than or equal to t is less than or equal to 1. So we know work is just the integral curve C, f dot dr. That should work in this case because these are pretty easy to compute. You don't really need to use any other method. This is our r of t, so our r prime of t, or dr, is going to be given by 4 minus, that's not really a good 4, 4 minus 4t, and subbing in our r of t into that, to get f of t, we're going to get f of, I guess, r of t equals, clarifying these are vectors, it's going to be 4t minus 2t squared and t. Okay, so now we just need to take the dot product of these two vectors and then integrate from 0 to 1. So 0 to 1, 4t minus 2t squared plus 4t minus 4t squared. That should be our dot product, dt. Combining our terms, we're going to get 8t minus 6t squared dt, same integral, 0 to 1. That is 4t squared minus 2t to the third power from 1 to 0. And that should just be 2. 12 is 2. Just to confirm, 4 minus 2 equals 2. All right.